So, welcome to this particular class. In the last class we did the integral analysis of the natural convection boundary layers, and we showed that what are the expressions for the Nusselt number under those two cases. Now, if you recall the two expressions, that for high Prandtl number, your Nusselt number expression was, if you recall your notes, raised to the power of 1/4 okay, into Rayleigh number to the power of 1/4. This is raised to the power of 1/4, this particular parameter. So, that was a high Prandtl number limit, right. So, if you look at this particular graph, for example, do not consider the lower one, consider the upper one, this particular graph, you can see that the high Prandtl number regime is something like this, right. So, that is the high Prandtl number regime. Okay. Similarly, in the low Prandtl number regime, we already showed through our scaling analysis and through the integral formulation that it is 3/8 1/4 q1 divided by 2 q1 plus 1 half Rayleigh number to the power of 1/4, right. So, that is the low Prandtl number regime, right. So, that would be this portion of the graph, right, with the merger point close to 1. Okay. So, at about 1 the two graphs will actually merge. Okay. So, as you can see in this particular case, of course, in the limiting values we have already said that what is the limiting value, that means when Prandtl number approaches infinity, right, when Prandtl number approaches infinity, the Nusselt number tends to become about 0.783 Rayleigh number y 1/4, right. So, it would go, this particular value will be about 0.783, right. Okay. On the other hand, when Prandtl number goes to 0, okay, the Nusselt number, okay, becomes 0.689, okay, into Prandtl number Rayleigh number to the power of 1/4. Okay. That is the lower bound of this particular graph. Okay. So, as you can see over here that the Nusselt number expressions match at around Prandtl number equal to 5/12. So, this point is not 1, it is about 5/12. This is the point where the two Nusselt number expressions that you see here and here, they basically show the same value, okay, a singular value, right, or very close to each other. Okay. So, they kind of merge, they show a match, okay, for these two values. Okay. So, of course, here the assumed velocity profiles okay, are identical for q1 and q11 equal to 1. Okay. That is the case. Okay. Now, in this particular case, okay, you can see that the Nusselt number to a certain extent depends on the analytical forms of the velocity and the temperature expressions, right, that there is some dependence. Okay. But when we choose a velocity profile or a temperature profile, there is always that trade off, okay, and that trade off we will see how much is that trade off when we actually do our similarity solutions, okay, because our similarity solutions will give you that kind of a profile. Okay. So, the similarity solution in itself, okay, has got that extra bit that it can predict the exact shape, okay, of the profiles, but this is also pretty reasonable from the two equations. Okay. We have been able to get the two expressions and we have been able to put them in the same plot, and this is the point where the merger actually happens very close to 1 kind of, okay, and or 1ish, and from the two sides you get the two families of curves, right. Okay. So, these are the important factors that you should keep in mind before we move on to the similarity solutions now. Okay. So, let us go to the similarity solution now. So, the similarity solution here will use some of the similar arguments that we have used earlier. Okay. Here of course, you see that there was a peculiar thing coming out of it, that delta by h was scaling as Rayleigh number to the power of 1/4, right. So, that provides, like we did in the case of your flat plate boundary layer, remember there was delta by x was scaling as Reynolds number to the power of half, right. So, that was the expression that we got earlier. So, there what scaling did we do? We did the scaling with respect to that, right. Okay. So, here also we will use something very similar, okay, in this particular case. So, so any length scale, the first point to note, any length scale of the boundary layer region okay, is proportional basically to y to the power of 1/4, that is what we have seen. Okay. So, the dimensionless variable can be constructed, okay, and it can be written as neta, which is a function of x and y. This is very standard, this neta form you have seen earlier also. It basically absorbs both the variations x and y and casts this in terms of one variable only. The validity of this expression will be proven that once we solve the equation and come to the final expression, right, it would be an ODE which would only be a function of this, right. So, that was the whole idea. Okay. So, the similarity variable, okay, this particular similarity variable can be written as x by y into Rayleigh number to the power of 1/4. This is very similar and intuitive if you have done your forced flat plate boundary layer expression, right. It is very similar in spirit to what we have done over here. Okay. And let us say Prandtl number is greater than 1. Okay. So, this is the most appropriate scale for the thermal boundary layer, right, because if you know delta T, the most proportional, it was proportional to something like this, right, this we knew, right. So, we have used that very scale over here to get to this similarity variable, right. So, that was the boundary layer thickness, right, if you recall that was what was done, right. So, delta was the height, okay, the delta was that particular height, right, of the boundary layer at any particular instance, right, where x was the direction. So, if you have forgotten, so this was x, that was y, correct, this was x, that was y. So, this x and y were like this. Okay. So, what it essentially means is that delta is basically whatever is the thickness at any particular y, right. So, that is how the scaling has actually worked. Okay. So, this particular thing we got from the scaling and also from the integral analysis we proved it. Now, what we are going to do, we are using this variable now, proposing this variable as the similarity variable over here, right. So, we also introduced the stream function. If you recall, you can solve this similarity solution in different ways. Stream function is one such approach. Okay. So, u is given by d psi dy and v is given by minus d psi dx. Okay. So, the equations become, so let us cast the energy equation. Okay. So, d psi dy dt dx minus d psi dx dt dy is equal to alpha del square t dx square, right. On the other hand, the momentum equation, which is basically the y momentum equation, d psi dy d square psi dx square plus d psi dx d square psi dx dy equal to minus gamma d cube psi dx cube plus g beta t minus t infinity, right. These are the two expressions that we had right earlier. This is just, there is no similarity transformation that has happened, it has been just substituted, that the u and the v profiles have been just substituted over here. Okay. Now, we note one other thing, say the dimensionless temperature which we can call theta in this particular case, which is basically T minus T infinity divided by T naught minus T infinity should be given as theta. Now, this theta should be a function of definitely neta, right, that is obvious. It can also be a function of Prandtl number, give or take, right. It should be a function of your Prandtl number as well. If you recall all the expressions that we did earlier, right, where we had Nusselt number and delta t and all these other things, you saw the Prandtl number dependence. Okay. So, this dependence may be actually not a major dependence, that we will also see whether this is a major dependence or not, right, but this dependence has to be incorporated into this, okay, into this particular form. Okay. Now, for Prandtl number greater than 1, right, we select the v velocity, which is the velocity along the y direction, right, as alpha by y Rayleigh number to the power of half into some function which is given as a function of once again neta and Prandtl number, right. So, Rayleigh number to the power of half, this we already knew, alpha by y Rayleigh number to the power of half, this was already there. We are just introducing this additional function, so that because we are not sure what is going to be the case, and of course, one thing that we know, this will be of the order 1, right, because if you recall your v expression from your previous scaling arguments, okay, you will find that it is alpha by y Rayleigh number to the power of half into some Prandtl number coming into the picture, right. So, this factor that I have said, okay, because if our scaling is accurate, then the prefactor which sits in front of it cannot be a factor which is more than 1, it should be of the order 1. So, this g that we have put over here is of the order 1, that much we can say, right. Okay. So, from the definition that v is actually equal to d psi by dx, right, we can write psi as alpha Rayleigh number y to the power of 1/4 f neta comma Prandtl number, where g is basically df by d neta. Got it? This is just for convenience, we have done it that way. Okay. So, this is the psi that we have. Now, what is remaining? If you look at the previous expression here, everything is in terms of t and psi, right. Everything is in terms of psi or it is in terms of t, right. So, it essentially means in this particular expression what we have done, we have cast it in terms of theta, t has been cast in terms of theta, right, and psi has been cast in terms of Rayleigh number and the function f, right, that is all. So, essentially what we can do once we substitute all these things, okay, all the factors will actually go out, all the t, all the v expressions or all the psi's will be replaced by basically Rayleigh number, f, g and this kind of terms, right. So, that is what exactly happens. Let us move into the next page and show that okay. So, 3/4 f theta prime is equal to theta double prime, right. So, this is the expression that you get after the substitution. You can do all the math yourself, half f prime square minus 3/4 f into f double prime f triple prime plus theta. So, one is momentum, one is energy, right. So, that is what we have got over here. Okay. So, this equation, okay, 4.6, I mean this particular equation which in Bejan's book is 4.61, this equation is a balance between convection and conduction, which is obvious, right, that is what it is supposed to be, right, where the momentum equation, this is the momentum equation, right. Okay. So, is a balance between friction and buoyancy as Prandtl number goes to infinity, right. It's a balance between friction and buoyancy if the Prandtl number goes to infinity, because if you can look on the expression on that left hand side, Prandtl number is there in the denominator. So, it will be 1 by infinity, right. Okay, so, this part will just basically vanish, the left hand side. So, it will be a balance between the other two terms, right. So, this also agrees with what our scaling argument initially was, right, where we said that if the Prandtl number is very high, right, okay, it is a balance between friction and buoyancy, right. If the Prandtl number is very low, it becomes a balance between the inertia as well as the buoyancy. Buoyancy will be always there, right, if you recall those expressions. Okay. So, now what are the boundary conditions? So, the boundary conditions are important to solve this. So, at x equal to 0, u is equal to 0, f is equal to 0, right. Okay. At neta equal to 0, okay, that would mean v equal to 0, f prime is be equal to 0, t will be equal to t naught, theta will be equal to 1. Check all these things out, okay, it should be pretty self obvious, right. As x goes to infinity, neta goes to infinity, correct, okay. So, v goes to 0, t goes to t infinity, f prime goes to 0, theta goes to 0, right. Okay. So, this actually brings to the strategy, that means we have cast now the two general form of the equations, right, and we have also cast now the boundary conditions, okay, these two boundary conditions, these two sets of boundary conditions. Now, it is anticipated that you would just now solve these two expressions, okay, and there are lots of, we already discussed about it, there are lots of methodology, except for here it is f and theta both, right. So, that is how you have to solve it in a very coupled kind of a fashion. Okay. But there is no ambiguity in the solution, you have sufficient number of boundary conditions, you have the equations which are well posed, the expressions are ODEs in their own way, right. So, there is no problem as such in casting these particular forms, right. Okay. So, let us look at the what we get out of this, right. So, after the solution, this is what we would get, okay, for our Prandtl numbers, I mean you see the whole expression for all types of Prandtl numbers, we have exactly plotted it. So, the first one is basically theta, right, plotted against the similarity variable which is neta, right. A couple of key things that you see immediately, that as Prandtl number goes to infinity, right, or becomes very high, you can see that all these theta curves kind of merge with each other. Do you see that? All the theta curves seems to be stacking up. So, they tend to go towards one single curve, right. So, they are basically moving, as you can see there is a lot of difference when the Prandtl number is very small. This is Prandtl number 1. As you go on increasing the Prandtl number from 10, 100, 1000, okay, you see the curves are becoming very close to each other. So, they are stacking, right. So, for example, from 10 to 1000, okay, it is a Prandtl number of 2 orders change, right, but the graphs have not shifted at all, right. So, you can see what we can conclude, that the theta, if you talk about theta, okay, that the theta basically collapses onto a single curve, okay, as my Prandtl number approaches infinity, right. Why does that thing happen, right. Now, the question is that why does such a thing of Prandtl number, I mean why should this, all these Prandtl numbers should actually all the temperature profiles should actually merge in that particular way, right. So, why it should not why it should merge is because if you look at the corresponding Nusselt number profiles, right, if you look at the corresponding Nusselt number profiles and other things, you will find that when you actually have a high Prandtl number fluid, okay, there the Prandtl number dependence basically goes away, right. You have already seen that for high Prandtl number fluids, okay, really high Prandtl number fluids, the Nusselt number dependence does not have a dependence on the corresponding Prandtl number as such, and that is naturally appears in this particular expression, right. okay, because if you look at your Nusselt number is also given as it is a slope of this particular theta prime at neta equal to 0 into the corresponding Rayleigh number, right. So, that is what it is. Okay. So, you can already see that the collapse is significant, right. So, that means the scaling argument was correct, okay. It merges onto a single curve, okay, as we go on increasing the Nusselt number. Now, if you look at the corresponding G over here, which is basic and plotted once again versus this, right. Okay. So, so this is basically the velocity expression. Remember the velocity, this is V y by alpha into Rayleigh number to the power of minus half. So, here you can see once again that the peak in the velocity, right, these are the peaks in the velocities, right. These are basically the peaks in the velocity. They all happen when neta is of the order 1, right. This is also very significant because we said that when the Prandtl number is actually high, right, what will happen is that the peak of the velocity should happen at delta t, right, and delta t is basically your neta in this particular case, right, because neta and delta t is basically the same, okay, correct. So, that is what it is over here, that at neta equal to or the order 1 or by order 1, I mean just write about 1, okay, when it is around 1, okay, the portions of the velocity profile approach kind of a single graph. So, these also starts to stack up. So, if you draw the next profile, it will be somewhere like that, right. Okay. So, the dimensionless velocity peak is consistently of the order 1, that is one thing. So, this G, if you recall, we said that this will be of the order 1, right, if our scaling was correct. So, these are all characteristically coming out to be around 1. Okay. So, that means the scaling argument was correct to begin with, because all these velocity profiles now are exactly showing of the order 1, okay, to begin with, right. Okay. So, this is a significant finding, and it also shows that our scaling argument was actually the right one, okay. And the velocities seem to peak around neta equal to 1, which is also predicted in that sketch that we made, okay. And it also showed that all these velocity peaks are kind of merging towards the same profile as we go on increasing the Prandtl number, right. Okay. So, all these things are very significant arguments over here, okay. So, let us look at, go back to our sheet, and the local heat transfer coefficient H y by k is equal to minus theta prime neta equal to 0 R A y 1/4, right. So, when Prandtl number goes to infinity, Nusselt number becomes 0.503, Rayleigh number to the power of 1/4, right. When Prandtl number goes to 0, Nusselt number becomes 0.6 into Rayleigh number y, Prandtl number to the power of 1/4, right. This is very close to what are the values that we got from our integral formulation, right. The average Nusselt number, these are the local Nusselt numbers, right. The average Nusselt number is when you integrate it from 0 to h, that means along the length of the plate, this becomes 0.671 into Rayleigh number, sorry, this will be now Rayleigh number h to the power of 1/4 as Prandtl number goes to infinity, and this will be 0 to h is equal to 0.8 into Rayleigh number, Prandtl number 1/4 as Prandtl number goes to 0. Okay. So, this is what we got earlier, okay. This is the local, okay, and it comes out to be pretty close to what has been predicted by the integral formulation. So, we can see from this exercise, okay, that how just by using the similarity transformation in a very similar way like what we did in our flat plate boundary layer forced convection part, we are able to get the similar form over here as well. So, you can also see one other thing if you look at this table now, okay. So, here you can see this is the basically whatever I said, okay, for different Prandtl numbers we have noted down the values, right, of the Nusselt number, corresponding Nusselt number, okay. So, as we can see that when Nusselt number is of the order of infinity, this comes out to be around 0.5, which is what we predicted, right. Okay. And when Nusselt number is very small, okay, this becomes about 0.612, taking into account the Nusselt number into consideration, right. When Nusselt, so basically as you know, the Nusselt number is about 0.6 into Rayleigh y into Prandtl to the power of 1/4, right. So, this corresponds to this, right. So, if you put whatever is the value of Nusselt number here, that is say 0.01 raised to the power of 1/4 and then multiply it by 0.6, this is the kind of value that you are going to get. Okay. So, as you can see, but one couple of interesting things that you can note out of this exercise is that when we change the Prandtl number from 2 all the way up to 1000, right, that is almost order 3 change, okay, or let us take 1 to 1000, that is proper order 3 change. This Nusselt number values, the prefactor changes from 0.4 to about 0.5, right, 0.4 to about 0.5. Okay. So, that would roughly translate to not a very significant change, about 15%. Okay. So, we get about 15% of that order kind of a change, 15 to 20% change when the Prandtl number varies by 3 orders, right. So, and if you observe now between 1 and 10, okay, this change is even minuscule, right. So, 1 is for example for air, it is about 0.72. So, it is roughly of the order 1, right, and on the other hand for water it is about 5 to 6 ish. So, there is not much of a difference. Okay. So, this would mean that the Nusselt number is a much, remember when we started this exercise we said that our f or the function, right, which depends on neta as well as Prandtl number, we actually said that that Prandtl number dependence can be a weak dependence, and it is actually shown in this calculation that indeed that Prandtl number dependence is pretty weak, because we are changing the Prandtl number quite a bit, the result is changing by a very small amount, right, as long as you keep your Rayleigh number to be the same, right. If your Rayleigh number changes, okay, there is a huge change, because it's you can see it's Rayleigh number to the power of minus 1/4, right. So, it is a huge change. So, it is a weak dependence on Prandtl number. This also satisfies one other requirement, that for example, if you are trying to, for example, carrying out experiments with water is much easier than carrying out with air, because air being gaseous and all those things. So, people can get away, they can conduct experiments with water and still they can use the same value for air, because the change is not more than like about 10 to 15%. So, you know the exact error is not that much, and you can live with that error. So, you can do the work in a much benign system like water, which is easy to handle, okay, or vice versa, depending on which kind of problem you are looking at, and still you can get away with it. Okay. So, this is the most interesting part that has come out of this particular exercise, okay, that you can actually have this kind of behavior, okay, where we have clearly established Rayleigh number dependence is much stronger than the corresponding Prandtl number dependence. Okay. See you in the next class with the next feature, which will be on uniform heat flux.